All right, so we're going to talk about random variables and probability review. And so again, this is, of course, about modeling financial data. And the primary thing that we're going to be looking at are asset returns. And when you think about an asset return, we went over return calculations before. Say we're investing in Microsoft stock. We buy it today. We hold it for a month. 1 month from now, we sell it. We can calculate the percentage change in price. That's the rate of return. But from the point of view of today, the rate of return on this 1 month investment is not known because we need to know what the price next month is in order to be able to calculate that return. So we can think of the rate of return as a random variable because the future is not known and the return depends upon the future price, which is not known. And so the outcome is uncertain. And so we can characterize returns as a random variable, which is a variable that can take on a possible set of values called the sample space. So the future price could go up, it could go down, and so there's a potential list of values of the future price. And then we attach a probability to each of those prices, and that gives us the probability distribution over those potential values. So what we're going to review today is various mathematical ways of describing random variables and distributions, and with several examples towards thinking about asset returns and the properties of probability distributions for asset returns that look reasonable. So some examples. Typically, an uppercase letter denotes a random variable. So uppercase X, in this case, is the price of Microsoft stock next month. It's a random variable because we don't know what the future price is going to be. What's the sample space of the future prices? Well, the sample space, this is the possible values that we think the prices can take on. Now, prices can't become negative, so we know that the sample space is going to be those, say, positive values. And if the stock is trading, if the stock doesn't go out of business, then the price should be positive. Now, prices can't go up to infinity, so there's some realistic upper bound on prices. And that upper bound might be $1,000 or something like that. So we can think future prices can lie anywhere, any real number, say between 0 and some big number m, like 1,000. So that would be a characterization of a random variable, the future price, and its sample space. Another random variable could be the rate of return on the investment, and the rate of return, which is the percentage change in price. Now, what is this appropriate sample space for a rate of return? Now, what's the smallest value that a rate of return can take on? The worst you can do is lose all your money, right? So if you buy Microsoft today for 30, and if Microsoft goes bankrupt and its price goes to 0 in the future, then the percentage change in price is minus 100%. So the returns are bounded from below by -1, so they can't be any more than that. And the upper bound, again, is some big positive number. If, say, Microsoft, I don't know, invents some product that revolutionizes the world, and its price is going to shoot up, and but it's not going to go off to infinity. So there's some reasonable upper bound associated with that. Another random variable we can think of, and that's used a lot in probability modeling in finance, is just a discrete random variable that just takes on two values. So we're going to set x to be equal to 1 if the stock price goes up, and we'll say x is equal to 0 if the stock price goes down. So this is sort of like a coin flipping example. You flip the coin, it lands heads, that's like the stock price going up. If the coin lands tails, it's like the stock price going down. And then we're just coding the random variable to be 1 and 0 based upon those events. And here the sample space is very simple. It's just two values, 0 and 1. So those are examples of random variables that we'll be looking at. So once we have these random variables, we need to characterize their probability distribution. Now, in probability models, we usually distinguish between what are called discrete random variables. And a discrete random variable is a random variable that can only take on a finite set of values. So in the last example, the up-down indicator, it took on two values, 0 and 1. That's a discrete random variable, and its sample space is two discrete points. Okay? The probability distribution of a discrete random variable is a function, say p of x, such that p of x is the probability that the random variable is equal to little x. So typically in notation, capital letter denotes the random variable, and a lowercase letter denotes a value in the sample space that the random variable can take on. Okay. Now, this probability function must satisfy certain conditions in order to be a valid probability function. So probabilities are greater than or equal to 0 for all values in the sample space. Probabilities are equal to 0 for values outside of the sample space. We assume that all the values in the sample space, again, are discrete, distinct points. The sum of the probabilities of the values in the sample space is equal to 100%. And probabilities have to be less than 1 as well. So as an example of a simple, discrete random variable and a probability distribution, here's a case where we can have a random variable x here, and x is going to denote the annual rate of return on Microsoft stock. All right, so we have a random variable x that's going to represent the annual rate of return on Microsoft stock. And this is an example that's kind of like the case where you might have a stock analyst who's working for an investment bank, and they're doing some fundamental analysis, and they need to make some forecasts of what the rate of return might be over the next year. And the analyst might have a very simplified way of viewing the world, that over the next year, the price of Microsoft stock is primarily contingent upon what's going to happen to the state of the economy. And so the analyst says, well, I think there are really 1, 2, 3, 4, 5 potential states of the economy. Depression, that's a very bad state. And if the economy is in a depression, then Microsoft is going to lose 30%. And the analyst puts a probability of 5% on that event occurring. And then the other state of the world could be, say, a recession. And if a recession happens, then Microsoft has an annual return of 0%. And the analyst puts a probability of 20% on that. And then similarly, normal, mild boom, major booms. These are other states of the world. And then we see as the economy gets better, the rate of return goes up. And then we have these probabilities. So notice that the normal state of the world is the state that gets the highest probability associated with it. Now, this is a valid probability distribution. All the probabilities are between 0 and 1, and the sum of all the probabilities add up to 1. Okay. Now, in this case, where do these probabilities come from? In this case, the probabilities are the subjective beliefs of the analyst. They may have nothing to do with the real world, in quotations, but they're just, views or opinions associated with the analyst. In probability theory, there are generally two types of ways that we view probability. One way, the subjective approach, is probabilities are opinions or degrees of belief. And this is associated with what is often referred to as Bayesian statistics. Okay? The other approach views probability as of actually real, physical, objective things. So the objective view of probability, think of the coin flipping example. So if you have a fair coin, that is, it's weighted such that the probability that the coin lands heads or tails is 50%. So where does that probability 50% come from? Well, it's an objective feature of the coin and the experiment of flipping the coin. And the idea is that, when you flip a fair coin, and you do this in an experimental setting, say 1,000,000 times, the probability that the coin lands heads is the fraction of times in the experiment that you actually observe the coin landing heads. And the probability that it lands tails is the fraction of times you actually observe the coin landing tails. So there you think of probability as being a property of the coin, the experimental setting, and something that you can repeat over and over again and reproduce. Whereas the opinion approach is, there's no experiment going on here. You can't repeat the idea of the views going over and over again. It's just a degree of belief. Okay? Both views of probability theory are equally valid, and but within the statistics literature, there's often very strong opinions about what is the right way or the superior way to view probability. In this class, we won't make a judgment on that, but we'll essentially just take probabilities as given and do computations. So one of the things I want to show you is an Excel spreadsheet that I have. And now Excel is not necessarily a good tool for doing probability calculations. And so the point here is just to illustrate how to do certain computations in Excel and show some show graphics and things like that. R is a much better environment for doing probability calculations and so on. But for my case, I have my example. I just put out an Excel spreadsheet. I have my returns. I have my probabilities. And then I can do a nice simple bar chart to represent the probability distribution. So in the graphical representation of the distribution, I put the values in the sample space on this axis, and then the heights of the bars just represent the probabilities. And so from this graphical representation, we can clearly see the most likely value is around 1%. The shape of the distribution is symmetric in that this is the middle of the distribution, the shape to the left of the middle, and the shape to the right of the middle is the same, and so on. We can do the same computation in R. So here's my, this is new. This is, again, just based on the examples in my lecture notes. So if I wanted to plot the probability distribution in R, I would just create a vector of values that represent the values in the sample space, create a vector of probabilities, and then do a bar plot. And that gives me the values here. Okay. A more mathematical model for a discrete random variable is based on what's called the Bernoulli distribution. And the Bernoulli distribution is a probability model that essentially describes the coin flipping experiment. So we have two mutually exclusive events, generically called success and failure, right? So in modeling stock prices, a success event is the stock price goes up. A fail event is the stock price goes down. That's assuming you have a long position in the asset. If you have a short position, then stock price going up is the failure, and the stock price going down is the success. So in investments, the long position means you buy something today, you hold it, you sell it in the future. A short position means you sell it today, and then you buy it back in the future. Okay? And so when you're long something, you're hoping the price will go up. When you're short something, you hope the price is going to go down. Typically, shorting works, just as an aside, because this is going to come up later on. When you short a stock, typically you open a brokerage account in, like at Fidelity or E-Trade or something like that. Say you want to short Microsoft. Well, you're going to sell something you don't own. So how do you do that? Well, if you have a brokerage account, you can borrow the stock from somebody who owns it. And you borrow it, then you sell it, you get the proceeds. Okay, you hold on to it. But because you borrowed it, you have to give it back at some point. So when you close out the short position, you go back in the market, you buy it back, and then you return the stock to who you borrowed it from. So you want to think of that transaction as taking place when you do a short sale. Okay. All right. So we're going to call this, go back to the Bernoulli example. Let's say x is equal to 1 if a success occurs and x equal to 0 if a failure occurs. Okay, so that's the coin lands heads, success, coin lands tails, it's failure. Now the probability that we have a success, that x is equal to 1, is going to be equal to pi, and pi is some number between 0 and 1. And then the probability of a failure, that x equal to 0, is then 1 minus pi, right? Because we have two events, the sum of the probabilities have to add to 1, so pi plus 1 minus pi is equal to 1. Now, a simple mathematical model for this probability distribution, or p of x, we can write as pi to the x times 1 minus pi to the 1 minus x, where x only takes two values, 0 and 1. So this p of x function gives us our probabilities. Notice that when x is 0, p of 0 is pi to the 0 times 1 minus pi to the 1 minus 0. So that's 1 minus pi. So that we have pi to the 0 is 1, 1 minus pi to the 1 is 1 minus pi. And then when x is equal to 1, my p of 1 is pi to the 1 times 1 minus pi to the 1 minus 1, so that's equal to minus pi. So this very simple mathematical representation gives us our probability function for the Bernoulli distribution. Now, the other type of random variables that we look at are called continuous random variables. A continuous random variable is a random variable that can take on any real value. All right? And so now when we talk about the probability density function of a continuous random variable, we're going to have a probability function that we're going to denote as f of x to distinguish it from p of x for the discrete random variable. And this f of x represents what's often referred to as the probability curve. Okay? Now, the probability curve satisfies such that if a is any interval on the real line, the probability that the continuous random variable is in this interval is equal to the integral of the probability curve over that interval. So, in other words, the probability that x is in this interval is the area under the probability curve over this particular interval. So we have a continuous random variable, we have a probability curve, and probabilities are associated with areas under the curve. Now, this probability curve must satisfy, it's always positive, because we want to compute area under a curve, and the total area under the probability curve is equal to 100%. So that's the idea, is that all the probabilities add to 1. So if we think of a probability curve here, let's say x is a continuous random variable. Here's its probability curve, and I've written this suggestively like a bell-shaped curve, like a normal distribution, which we'll talk about later. And we want to say, what's the probability that this random variable is between minus 2 and 1? So our interval is between minus 2 and 1, and the probability of this event is equal to the area under the probability curve over this interval. So we see that one of the reasons why probability theory with calculus is useful, because in order to calculate probabilities, we have to find area under a curve. In order to find area under the curve, we have to integrate the probability function. So when you take a more mathematically oriented probability theory course, you do a lot of calculus to do these types of calculations. In this class, we're not going to do the calculus calculations. Right? We need to know the concept of doing this. And then even if we ever have to integrate something, we can do it in R numerically. So if we have a function, we want to find out the area under the curve, we can write a function in R to represent the probability curve, and then we can use a function called integrate to numerically calculate the area under the curve for us. So we're going to be using tools that will do calculus for us, but we just need to know the concept of what's going on. All right. A very simple example of a continuous random variable in a distribution is the so-called uniform distribution over the interval AB. So we say x is distributed uniform. So this is a bit of notation in probability theory. X represents a random variable. This little squiggle character is to be read as is distributed as. So x is distributed as uniform over the interval AB. Okay? The probability curve of the uniform distribution is a rectangle. So if we want to think about the uniform distribution, we have some interval A to B, and we know that the area under the probability curve has to equal 100%. And the idea of a uniform distribution is that, probability over any interval of the same length is the same. Okay, so it's a way of thinking of like equal probability for events of the same size, so to say. So if this total area has to be 100%, then we know that length times width is equal to 1. So the height of the probability curve is 1 divided by b minus a. So that represents the probability curve for a uniform random variable. And we know that this probability curve is greater than or equal to 0, provided the right endpoint is bigger than the left endpoint. And we know that the total area under this curve, length times width, if we do the integration, it's equal to 1.